Right, so without further ado, let's start. Okay, so good morning, everyone. I presume that you have another, like a briefing going on in parallel together with the session, but maybe not all involved. Okay, but that's okay. If you cannot make it, then you can always watch the recording again inside the My Times. So in My Times, if you go to My Times, I need to log in. Okay, there is a recording for all the lecture sessions in the class. Alright, so I will show you later. Okay, so now as a reminder, before we start, your practical test or S1 and practical test or S2 are due to be submitted latest by this Sunday. Okay, so please make sure you submit before Monday. Okay, if you do have any problem, as I mentioned, please ask in the group. Okay, please refrain yourself from personally WhatsApp me because I may not be able to respond to your personal messages. Right? Okay, so now let's look at the next chapter in the OS. Another important concept that you need to understand is the memory management. How the operating system manage memory. Okay, because remember, in your system, you have so many processes running at the same time. Am I right? And then so how the operating system makes sure that all these different processes will have access to the memory, to your RAM, okay, and to your secondary storage. Okay, so this is another important task of operating system. All right, so now let's look at I just introduce you first to the three main important terms, okay, in memory management, right? So first you have what we call a frame. Okay, so a frame here means in your RAM, in your main memory, okay, your main memory will be divided into a fixed length block. So you will have several blocks inside your RAM, your main memory. Okay, and then you might also have a page. Okay, so what is page? Right, a page is a fixed length block of data. Okay, it's contain data that resides in secondary memory. Okay, in your hard disk drive or in your USB. Okay, you might in your USB drive or your hard disk drive, you will have a fixed length block, several blocks, and that blocks will contain data. Okay, so we call the block as page. Okay, the block in the main memory we call it as frame. All right, and another important concept here is segment. Okay, so what is segment? Okay, so segment again is a variable. It's not fixed. It's a variable length of data. Okay, that again resides in the secondary memory. Okay, meaning that the segment exists inside the hard disk or USB drive, the secondary memory, and the length of the block is varies depending on the size of the data that you have. Okay, so these are the difference between frame, page, and segment. Okay, so now let's move on to the next one. Right. So when it comes to managing memory, okay, so remember your memory is very limited. So may I know what size is your RAM at the moment in your machine? 8 gig? 2 gig? 2 gig will be very slow. 4 gig? Can you check on average your RAM? Do you know how to check your RAM size? So what is the size of your RAM at the moment? 16? 24? Anyone have any idea how big your RAM is in your memory? The bigger your RAM, your PC will perform much more better. All right. So so you have a very limited access to these resources. Okay. Definitely, there must be some form of mechanism to manage access to these limited resources. All right. So when you when you manage the memory, the mechanism must be able to satisfy these 5 requirements. Okay, first is relocation. So what do you mean by relocation? Relocation, protection, sharing, logical organization, and physical organization. Now, relocation, right? So you have many active processes running in your machine. It will be residing in one of the blocks in your main memory. Remember, the blocks are limited, all right? So when there's a new process coming in, it should be able to swap, okay, to swap in and out of main memory active processes in real time. So when the memory is already full, so let's decide which page in the block that we need to swap out and bring in a new one. Okay, so that's what we meant by relocation. So OS should be able to manage the relocation. Right. Okay. And now you have protection. Okay, protection here. So what does it mean by here protection? Processes also need to acquire permission to reference memory location for reading or writing purposes. Okay, for example, the data in your hard disk should be protected. Okay, so if the process would like to acquire a reading or writing on that particular block, it needs permission. You cannot simply go and write anywhere in the disk. Okay, so the block in the main memory and the block inside your secondary memory should be protected. Okay, so access will require permission. Right, another one is sharing. Okay, sharing. Right, for example, in my Chrome, okay, I open my Chrome, or even here, I open my WPS Office Suite, and inside here you can see I have so many tabs opening. Okay, but you only have one process, big process, main process here, which is WPS. So the WPS application code are running somewhere inside the main memory. So when I open a different tab, this different tab should be able to access the same program code. Okay, so that's what we meant by sharing. So sharing here, okay, is the mechanism where the OS will allow each process to access the same copy of the program, okay, rather than having their own separate memory for the program. Okay, so you open one WPS suite, every time you open a new Word, okay, a new PowerPoint, when you open that new file, the file will always execute the same WPS program code. Okay, so that's what it means. It shares the same program code across the processes. Okay, and then we have what we call logical organization. How do we organize the block? Okay, so memory is organized in the linear fashion, okay, whereby programs will be written in the in modules, in smaller chunks, smaller portions, okay, and they'll be written and compiled independently, okay, and you will place them in the linear fashion. Okay, we will see this later, how it will be organized. And then you also have physical organization. Okay, so you have logical organization, how the OS will remember where the processes and data are being placed in the memory. The physical one are referring to the actual placement of the data and program on the disk, okay, on the hardware itself. Okay, so in the hardware here, right? So for the physical organization, programmer does not need to know how much space will be available, okay, on the disk, right? And they cannot leave the programmer with the responsibility to manage memory. So basically, the OS will be responsible to decide where within the hard disk it will place the program code and also the data, okay, for physical organization. All right, so now let's look at another concept here, partitioning. Okay, so some of you can partition. When you create your new virtual machine, when it comes to the hard disk, okay, when you install the Ubuntu or Kubuntu, it will ask you whether you want to erase all the disk and just create one partition, or you want to do partitioning. Okay, meaning that you want to break your hard disk into several different segments. Okay, so that is partitioning. So here, so this one, there's several techniques that you can use to partition your memory. Okay, so the partitioning one is the simplest one. It is used in several variations, and in somehow now it becomes obsolete in many of the operating system. Okay, so another way to partition is to use a virtual memory, something that what you did when you install your Ubuntu. You can decide either you want to erase the disk and just create one partition, or you can create different partition with different drive. Okay, so that one is partitioning. Okay, so now we look at the different type of partitioning. Okay, so there are several different types of partitioning here. One is the fixed partitioning. Okay, where main memory is divided into a number of static partition. Okay, you also have dynamic partitioning. Okay, partitioning are created dynamically depending on the size of the process or data. Okay, you have simple paging. We will look at this later. Simple segmentation. Okay, so we only focus on the first four. Okay, we will not discuss the virtual memory paging and virtual memory segmentation. This is another topic. Okay, which is beyond our interest. Now we look at the fixed partitioning. Okay, for fixed partitioning, you have two options. Either you can partition, you can create a block of the same size. Okay, for example, here you have 64 megabyte memory, and then you create partitions with equal size of 8 megabyte each. Okay, so you have fixed partition. You can also have unequal size partitions. Okay, so whereby you can create from the small partitions and then up into the bigger partitions. For example, here you have 2 megabytes partition, and then you have 4 mega, 6 mega, 8 mega, and it will increase. Okay, to the size that you will require. All right, so you have two options to do fixed partitioning. All right. Okay, what is the disadvantages for this fixed partitioning? Because this is fixed. All right, this is a fixed partition. So in the case where you have a process that is big enough, for example, a process come and it requires 20 megabyte. So there is no place you can put the process. Okay, so it will be limited to a process that has at least the maximum size of the partition. Okay, so there is another way, which is using overlay. You will need to design the program. And in this case, memory utilization also will not be efficient. Why? Okay, any program, regardless of size, will occupy the entire partition. Okay, so let's say the 20 megabyte just now. Okay, where do you can put the 20 megabyte? You can break it into two. So the first 16 megabyte, you place into the 16 megabyte block, if I use unequal one. And the remaining 4 megabyte, right? I can place inside the 4 megabyte block. Okay, so now the process are in two different partition in the unequal size memory. Okay, so this is one of the advantages. Another disadvantages is internal fragmentation. This one you have to know as well. Okay, do we have sample here? All right. Internal fragmentation. Okay, what does it mean? Okay, it is a wasted space, okay, due to the block of data loaded being smaller than the partitions. Smaller. Okay. Let's say, for example, okay, can I edit this? All right, for example, I have a process coming in, okay, and the process is the size of 6 megabyte. Okay, and I have 7 6 megabyte processors. Okay, need to use the memory. I don't know why. Okay, so let's say I'm using the fixed partitioning, right? So I have 7 6 megabyte processors. So because it is 6 megabyte, so it can fit inside the 8 megabyte. Am I right? 8 megabyte partition. So I will place the process here. Okay, so 1 megabyte, 6 megabyte process goes here. Okay, another one goes here. Okay, another one goes here. Okay, and so on. You can see, once you place the 6 megabyte here, can I draw? Okay. Okay, once I place the 6 megabyte here, let me see. Okay, this is a diagram basically. No. Hang on. Okay, oops. Okay, I placed the 6 megabyte there. Okay, the process. So I have the remaining 2 megabyte in the partition. Okay, so the remaining here would be 2 megabyte. So every time okay, let's see. Okay, I place a 6 megabyte process, then there will always be another 2 megabyte extra in between. Right? So the 6 megabyte goes here. Okay, and then another one, for example, okay, there will be another 2 megabyte extra in every partition. So you can see, in between the block now, you have a wasted space of 2 megabyte, empty space. So 6 megabyte occupied, 2 megabyte empty. Okay, 6 megabyte occupied, 2 megabyte empty here. Okay, and then 6 megabyte occupied, 2 megabyte empty. So within that block, within that partition, okay, there is one wasted space. So this wasted space is what we call internal fragmentation. Okay, the fragmentation that is internal to that block. Okay, all right. So this is the problem, okay, with fixed partitioning. All right. Okay, and then how do we arrange or distribute processes, okay, across the memory across the processes? Okay, so you can use multiple process queue, one process queue per partition. So the process will be queue, okay, depending on the memory requirement. Okay, and then the processes in the queue will be assigned the allocated partition. Okay, another way is to only use one queue, single queue, for all the partitions. Okay, regardless of the size. All right. So then later, the algorithm will look at the process in the head of the queue, and it will determine which partition should be allocated to that process. Okay, there must be some algorithms to help decide how we should assign the partition to the processes in the head of the queue. Okay, so these are the way, okay, to assign memory for the processes. Okay, so what are the disadvantages of using fixed size? Right, the number of partitions specified at system generation time will limit the number of active processes in the system. Okay, you can see inside this memory, the number of processes that you can run will depend on the number of partitions that you have. Am I right? Okay, so let's say here, if I have 7 partitions, it means that at one go, only 7 active processes can run. Okay, so another limitation just now, okay, is the small jobs. Okay, small jobs will not utilize the partition space efficiently. Hence, you will have more internal fragmentation. Okay, So this is the problem with fixed partitioning. So now, why not we look at dynamic partitioning? We don't fix the size of the block. Okay, we let it vary. Okay, partitions are of variable length and number. Okay, and process will be allocated exactly as much memory as it requires. Okay, so it is used in some of the server and system. Okay, so for example here, okay, you have a memory space, right? Okay, and then the portion here, 8 megabyte, is used for operating system. So you have the remaining 56 megabytes. Okay, process 1 comes in, and process 1 requires 20 megabyte. Okay, so we have all the free space here. So assign process 1 to this lot. Okay, so you have the remaining 36 megabyte. Okay, and then process 2 come in. Okay, process 2 require 14 megabyte. Okay, so assign this lot, okay, the next lot here. So the remaining would remain 22. Okay, and then process 3 comes in. Process 3 require 18 megabyte. Okay, so the remaining one can fit in process 3. So process 3 will be allocated the next block. Okay, the next space, I would say. So you have the remaining 4 megabyte. For example, okay, let's say process 2 already completed execution. So process 2 is pull out from the memory. So you have this space empty. Okay, so let's say we have process 4 comes in. Okay, and process 4 requires 8 megabyte. So looking at the space here in E, you have 2 empty space, right? So one is 14 megabyte, another one is 4 megabyte. Okay, so process 4 require 8, so definitely this space can fit in process 4. Okay, so you put in process 4 inside. Okay, and then process 1, for example, completed. Okay, this space is empty. And process 2 come in again, requires 14 megabyte. Okay, so definitely this space can fit in process 2. But you can see, by using this variable length, you will also face the same challenges, which is fragmented space. Okay, some space in between the processes are kind of wasted. Okay, but because this is fixed, this is dynamic partitioning, there is no specific block designed for it. Okay, so we call this fragmentation as external fragmentation. Okay, because the fragmentation is not dedicated to any or associated to any fixed size block or partition. Okay, so we call it external fragmentation. Okay, because the wasted space is external to all partitions. Okay, and as it grows, your memory will become more fragmented. Okay, so you need to know the difference. Internal fragmentation, you only have it when you have a fixed size partition. When you use fixed partitioning, either equal size or unequal size. Okay, you will have external fragmentation when you are using dynamic partitioning. Okay, all right. All right. So for external fragmentation, in the dynamic partitioning, the memory, okay, as your system grows, you have more processes, your memory will become more fragmented, okay, as eventually, all right? And of course, when you have more fragments, okay, the utilization of your memory will decline. Have you ever tried to defragment your hard disk? Not yet. Okay, not yet. It's probably 1 or 2 years down the road, you will have to defragment your hard disk because there are so many wasted space in between, right? And it will decline, it will reduce the performance of your system. So how to overcome this external fragmentation? Okay, one way is to use compaction. Okay, compact. Okay, what does it mean by compact here? This is a technique to overcome external fragmentation. Okay, whereby what happens is that the OS will shift processes so that they are contiguous. Okay, so free memory is together in one block. Okay, so what happened is when at certain stage, the external fragmentation has become worse, okay, probably going beyond the some benchmark, the OS will shift. Okay, it will copy the process and shift and put it contiguously. All right, so at the end of the day, all the wasted space or all the free memory will be available at the end here. Okay, so that's what we call compaction. Right? So, but of course, it is time consuming to do compaction because the processor will need to shift all the processes in your hard disk, okay, at one go. This is something that you will see when you do your hard disk defragment later. Okay, one down the road. Okay, it will not happen in 1 or 2 hours when you defrag your hard disk. Okay, now you have, I think, bigger 1 terabyte. It will take hours or maybe overnight, okay, to complete the compaction. Okay, right? Okay, so now placement algorithms. How do we select? How the OS select where to place the process? Okay, within your memory. Okay, so there are 3 placement algorithms, right? Best fit, first fit, and next fit. Okay, best fit, it chooses the block that is closest in size to the request. Best. Which one is the best fit? First fit, okay, it begins to scan memory from the beginning. Okay, and chooses the first available block that is large enough. Okay, and the next one is next fit. Okay, next fit means it begins to scan the memory from the location of the last placement. Okay, it finds where is the last placement happen, scan from there, and chooses the next available block that is large enough. Okay, now we look at one sample here. Okay, this is before. There are 2 diagrams here. So you have a before memory. Okay, so in the before allocation, okay, initial allocation, these are the empty spaces. Okay, the grey one refers to the allocated block, and the white one refers to the free block. Right. So now you need to decide where you need to place the new process, okay, inside your memory here. Okay, please take note that here you have last allocated block. Okay, this one is the last placement that happened in the system. Okay, so this one is the first empty space is 8 megabyte, second one is 12 megabyte, another one is 64, 18, 8, 6, 14, and 36. Okay, so now let's see here. We need to allocate a 16 megabyte process, okay, for the process, megabyte space. Okay, using first fit. Okay, first fit means it will scan from the beginning of the main memory, okay, and it find or it choose the space that is large enough, okay, to fit in the 16 megabyte process. So you can see here, okay, starting from the beginning, 8 megabyte does not fit, too small. 12 megabyte does not fit, too small. Okay, and the next one, 22 megabyte. Can it fit in 16? Yes. Okay, so it will put the 16 megabyte space. We allocate the 16 megabyte space for this process. So this is first fit. Okay, so the process will be placed here. Now, best fit. Okay, how does best fit work? It chooses the block that is closest in size to the request. How does it do that? Okay, so what happened for the best fit, the OS will do some extra work. Okay, so this is how the algorithm for best fit work. It will choose the smallest space, and then it will try to match the amount, the required space. It starts from the smallest. Okay, which one is the smallest? 6. 6 megabyte. Can it fit in 16? No. Okay, and then the next one, the largest one, 8. Okay, we have 2 8 here. Still cannot fit in. Okay. And then we have the next larger one, 14. Okay, 14 also cannot fit in. Okay, and the next large space is 18. Okay, so 18 can fit in 16. Right, so therefore, this space, 18 megabytes, will be allocated for the process using best fit. Okay, so for best fit, it starts by inspecting the smallest space. And then it grows until it finds the best fit. Okay, the best space that can fit the process. Right? Okay. So you can see for best fit, it will place the process here. Okay, it will place the allocation memory for this process here. Right, next fit. Okay, so next fit, you have to be alert, okay, where the last allocated block is. Okay, the last allocated block is here. So, for next fit, it will start scanning down the road from here. Okay, alright. Okay, so now, how does it work? It chose the next available block that is large enough. Okay, so from here, okay, the next free memory is 8 megabyte, cannot fit in. Okay, the next one is 6 megabyte, cannot fit in. And the next one is 14 megabyte, cannot fit in as well. Okay, this one. Okay, the next one is 36 megabytes. It can fit in 16. So using next fit, we will allocate this space for the process. Okay, this one is next fit. Okay. Alright, so clear. Right, do you have any question on these placement algorithms? Any question? Okay, yes. Next fit. Okay, next fit, you have to know where the last placement is. And usually in the question, we will tell you where the last placement is. Okay? So for next bit, you can see here, in the before figure, okay, the last allocated block is in here. Okay, this is the last allocated block. Right? So for next fit, we can read it again. It begins to scan the memory from the location of the last placement. So the last placement is here. Okay, this is the most recent space that you assign to another process. Okay, so for next fit algorithm, it will scan from here, not from the beginning. Okay, it will scan from here, starting from 8 megabyte. Okay, so 8 megabyte doesn't fit 16, 6 megabyte doesn't fit the 16, 14 megabyte does not fit again, 36 megabyte, yes, it can fit in this process. Okay, so therefore, using next fit, it will place or it will allocate this space, 36 megabytes, for this process. Okay, so the difference between first fit and next fit is that first fit scan from the beginning. It will always scan from the beginning. Next fit always scan from the last placement. Okay, so that's the difference. Okay, all right. Okay, any further questions? Nope. Okay. All right. Okay, so buddy system, I will skip this. Alright, so if you're interested to know about buddy system, you can learn about buddy system. Okay, but I will skip this buddy system at the moment. Okay, so I will go to the relocation. Okay, So when the fixed partition scheme is used, fixed partition of either equal size or unequal size, we can expect a process will always be assigned to the same partition. So usually the similar process will utilize the same partition, okay, in the main memory. Alright, but there are of course certain situations where, because your memory is very limited, you have to bring in a new process. So you need to decide which process need to go out. Okay, so to handle this relocation, okay, so we need to manage the addresses. The OS need to think about the addressing scheme, okay, between the process and the physical memory. Okay, so there are 3 types of addresses that you need to know. So one is that every single process, it will have what we call the logical address. Okay, so logical address is the address that can be comprehended by the OS. Okay, and it refers to a memory location which is independent of the current assignment of data to the main memory. Okay, so this is logical addressing. Something like your computer, you connect to the network, right? Okay, you have your IP address. Okay, so the IP address can change over time. You come here to the campus, today you have this IP, tomorrow you come to the campus, you get different IP. So the IP is used to recognize your PC within the network. So same thing for logical address. Okay, so this is the address used by the process. Okay, and then you have relative. Okay, this is an example of logical address as well, in which the address is expressed as a location relative to some known point. Why do we have relative here? So in your memory here, right, you assign a space. You assign a space. For example, this process start from here. Okay, can I draw? Okay, let me see if I can draw something. Hang on. Okay, for example, my process start from here. Okay, I don't know why. Okay, it starts, okay, sorry. It starts from here. Okay, and this is a space, maybe large enough. So to get to here, okay, for example, I want to get a data at this location. Here, okay, at this location. So definitely, I need to specify the relative location from the base, from the beginning. Okay, so it means that I need to specify the location, okay, from here to here. Okay, from here to here. So that's what we meant by relative. From the starting point to the location that I want to get the data from. Okay, because remember this is a space. Right, for myself, okay, let's say for example, I want to point to one of the students. From here, this is the starting point, okay, of the instruction. And then, how many chairs to go to, for example, one of the students? Okay, the lady there, alone. Okay, so there will be 4 rows of chairs to get to her. So that's what we meant by relative, okay, in the memory. Okay, so let's go back. All right, so you have relative addressing, and you also have physical or absolute main memory. So this is the actual address of every cell inside the memory. So this is something that you see 0x and some hexadecimal numbers. So that one is the location, the actual location of the cell inside the main memory. So there are 3 levels of addressing here, right? Okay. So why do we need to understand this address? Later we will see why. Okay, so now, right, so you have your main memory partition, right, into different frame. Okay, so frame is a fixed block, a fixed size block, okay, of that contain program or data inside your main memory. So you have your main memory and you divide it into a fixed partition. Okay, and each partition is called frame. Okay, you have frame number 0 until frame number 14. Okay, so the frame has fixed size. Another way to manage distribution of processes to the fixed size memory is you call pages. You also divide your process into smaller chunk, and that smaller chunk is called page. Okay, so pages refers to smaller size of process, and frame is available to the partition that you set in the main memory. Okay, so for example here, right, you have your main memory. Okay, and inside this main memory, you partition your memory into 15 available frames. Can you see from there? Yeah. Okay, let's say now you have process A. Okay, process A as well, it will be divided, okay, into several here, into 4 pages. Okay, so that it can be fit into 4 frames. Right? So process A has 4 pages, and then here process B has 3 pages, so therefore it will be occupy 3 frames. Okay. Process C has 4 pages, so it will occupy 4 frames. Okay. And then process D require only how many? Okay. Process D require 5 pages. 5 pages, 5 frames. It has 5 pages, so it requires 5 frames. Okay, definitely it cannot fit in the remaining one, right? It cannot be fit into frame 11, 12, 13, 14 because it requires 5 frames. Okay, so what happened now is that, okay, so using some algorithm, it will swap out the processes that use the last frame. Okay, it will swap out B, okay, because B only used 3, the minimum one. So let's swap out B and then put in D. Okay, but of course here you can see the D will acquire 5 frames, but they are segmented, okay, in different frames. Okay, segmented by C. Okay, you can see the first 3 frames or pages occupy frame 4, 5, 6, and the remaining 2 pages occupy frame 11 and 12. Okay, but as long as all the pages can be residing inside the same memory, although they are separated. Okay, so this is the assignment of process pages to free frame. So now, how the OS manage the information between the pages and the frame? Okay, so the OS will use what we call a page table. Okay, it will maintain page table. It will contain the frame location for each page in the process. Okay, all right. So this is used by processor to produce the physical address for the pages. You can see here. So for process A, it will have a page table for process A, right? So inside this page table, it will list down where process A are being stored. Okay, all right. So page number 3 here, okay, is placed in frame number 3. Okay, process B, all right. Process C, you can see up until 10. Okay, process D, page number 4 is in 12. Okay, and then, okay, so on. Okay, we will see this in the tutorial. All right, so I will move on to the next one. Okay, before we end. Another important part that you need to know, okay, is that because you have a very limited spaces, okay, limited spaces in the main memory, you have frame and you have pages. So you need to determine how you want to swap pages. Okay, there will be some algorithms used by the OS to decide, okay, which page in the frame that we need to swap out and replace with. Okay, So there are 4 algorithms here that we will use. Right? So first one, okay, there are 4, but I will discuss only 3. Optimal, least recently used, and first in, first out, FIFO. Alright. So for optimal, I will just briefly discuss, okay, and then we will do this in the tutorial. Okay, the optimal policy is you select for replacement that page for which the time to the next reference is the longest. Least recently used, which page that has been recently used. Okay. And the last one is first in, first out. Okay. So the first one that comes in will be the first one go out. Alright. So clock policy I will not discuss because this is another different types of algorithms. Okay, it's a bit more complicated. Alright, so I will discuss the simplest one. Okay, so let's say here you have one process and that process has 5 pages. Okay, page 1, 2, 3, 4, 5. Okay, and your memory only have 3 frames. You only have 3 frames. So one page can only occupy 1 frame. Okay, so that's the basic introduction for this one. Okay, so let's start with this. This is the page stream, okay, for the process. Okay, so the one that will be executed first is page number 2, and then 3, 2, 1, 5, 2, 4, 5, 3, 2, 5, 2. Okay, so it starts with the empty frame. So the frame is empty, so nothing in the memory. So the first page 2 there will be placed in the first frame. Okay? Okay, so 2 goes into the first frame. And then the next page is 3. Okay, so 3 goes into the second frame because the frame is empty as well. Okay. And then the next one is 2. Okay, 2 is already in the frame. So it's good. Okay. And then 1. Okay, page 1 is not in the frame yet, and the third frame is empty. So you bring in 1, okay, into the third frame. Now, 5. Okay, 5 is not in the frame, okay, and all the frames are already occupied. So how do we move out the pages? Which one should we select? Okay, so we see optimal. How does optimal works? Okay, so let's look at optimal. The optimal policy, select for replacement that page for which the time to the next reference is the longest. So it will look forward. And it will look at which frame or which page in the frame that will not be referenced in the near future. Okay? So the next, after 5 here, you can see 2 will be referenced here. Next. And then in 3 will be referenced here. Okay? And then the 5 will be next reference here. So which one is the longest to be referenced next? 3, right? 3. Okay, so therefore, so here you have 1. Sorry, you look at this frame. 2, 3, 1. You want to replace 5 inside. You want to bring in 5 inside. So let's look at this frame. Okay, 2 will be next reference here. Okay, 3 will be reference next here. 1, will there be any more reference? No referencing for 1. Alright, so it will be used just once. So 5 will replace 1 in this case. Okay, because there's no future reference for 1 anymore. Okay, alright. And then we have, okay, now we have 2. 2 is already in the frame. Okay, and then we have 4. 4 is not in the frame. So let's see. In the current frame, you have 2, 3, and then 5. Here. You want to bring in 4, right? So now let's look at the future. Okay, 2, when it will be referenced next? Here. Okay, and then we have 3. 3 will be referenced here, earlier than 2. And then 5 will be referenced earlier than 3. So the longest one will be referenced next is 2. Okay, so you will replace 4 in the frame that contain 2. Okay, so optimal look forward, LRU look backward. Okay, and FIFO first come, first in, first out. Okay, whoever come in first will go out first. The longest in the frame, basically. FIFO. Yes, FIFO will place the longest one. You can see here. Okay, you got 2. 2 is the longest. Then you will replace 5. And then here, next one, 3 has been the longest in the frame. You will replace with 2. Okay, so FIFO will replace the longest one in the frame, the longest pages in the frame. Alright, so I think I'll need to end here. So the rest we will discuss in the tutorial. Okay, let's update the attendance. It's a bit overwhelming. There are too many things, okay, to explain for this chapter. Right, so I will end the session. We will continue discussion on the algorithms in the tutorial. Okay, all right, thank you so much. Times there is actually a recording for every session of my class, so you can always watch the recording again for your revision. Okay, all right. So for those who are having problems with the installation, with the submission, please come forward. Right, thank you.